Hey guys, welcome back to another calculus video. Today I'm just going to be going over Stokes' theorem. So what is Stokes' theorem? Basically, it just relates a surface integral with a line integral. And let me quickly go over an analogy as to why that might happen why that might work. So let's say you've got a ball that's partially submerged in water and the water is very turbulent, which gives it a force field. So the surface that you're working with is going to be the surface of this ball that's submerged below the water. So this surface, it's not closed. It's open, okay? Because the top isn't influenced by any vector field, so you can just ignore it. The surface that you're going to be working with is going to be a partial ball, and that partial ball is the part of the ball that's submerged underwater. So basically, what do we associate curl with? Typically, we associate it with rotation, right? So basically, this is just as okay. Basically, this is like a really zoomed in picture of the ball at the point at the point that's that's just in contact with air and the water. So as you can see, there are some vectors that are acting on each small area element in that are sort of circulating. So what happens to the vectors that are acting at the edge of every area element is that they're canceling out. So basically there's some circulation there and there's some circulation there. And that causes these two vectors to cancel out. And the only vectors that don't cancel out are the vectors that are at the edge of the ball, or just at the boundary between what's below water and what's above water. So yeah, so basically what happens is all your vector all of your vectors cancel out, and you can actually evaluate this surface integral right here with a line integral which goes about the edge of the surface that is submerged underwater. So say if we had a Coke can, it's open at the top, and we wanted to prove Stokes' theorem for it. Basically what we would do is we would evaluate this surface integral for surface down here. So the surface down here, and then we would integrate, or we would evaluate a closed path surface integral about, let me switch colors, about this curve, so the edge. All right, I'm just gonna go straight into an example. So we're gonna prove, so basically my professor didn't go over what Stokes' theorem was really for, but he's just gonna ask us to prove it, to like prove this relationship on our final exam. So that's what I'm gonna go over in this video. So yeah, like I said, the surface integral should be set up about the surface, and the line integral should be set up about the edge of the surface. So this is going to be a cone. We're just going to say that it can be modeled by the equation z equals x squared plus y squared underneath the square root, and that it goes from z equals 0 to z equals 3. And we're just going to say that the top is open for the sake of this example. So let's try to work out the line integral first. So the line integral it'll just be a circle with radius 3 at z equals 3. So r is equal to 3 cos theta, 3 sine theta, 3. we can easily parameterize that curve just like that. And because we're going to need its derivative in our line integral, we'll just look for that. We'll just solve that right now. So the x component becomes negative 3 sine theta, the y component becomes 3 cos theta, and the z component becomes 0. So then the next thing we're going to do is we're going to substitute these values into our vector field. Y is just 3 sine theta. Negative x squared is negative 9 cosine squared theta. And we don't care about the z term. The reason for that being that we're eventually gonna dot these two values. And if the z component of this is 0, then it won't matter what the z component of our vector field is, because it's just gonna zero out. Okay, so this is usually how a surface integral looks like. We can let this equal to f dot the derivative multiplied by d theta. And it's going to go along, and we're going to integrate along the curve. So the vector f, or like these two dotted, makes negative 9 sine squared theta. Just multiply these terms. Now we're going to multiply these, which should give us negative 27 cos cubed theta. Okay, so then you can plug it into here. I'm not going to write it again. We're integrating with respect to theta. It goes from 0 to 2 pi because we're making a circle, right? Okay. And if we look at our integral table, the square root of sine theta works out to be 1 over 2 theta minus sine 2 theta divided by 4. And we're going from 0 to 2 pi. And the second integral works out to be 1 over 3 sine theta cos squared theta plus 2. Goes from 0 to 2 pi. This term cancels out because sine and pi is 0, always. This evaluated at 2 pi gives us negative 9 pi. Now this just zeroes out, because sine 2 pi is 0 and sine 0 is 0. Okay, this is the reason why all of this zeroes out. So the answer is negative 9 pi. So that's what our line integral is equal to. That's the right-hand side of the Stokes theorem equation. Now we're going to try to evaluate the left-hand side, which is a surface integral. Okay. Just going to copy these down. All right. Start off by finding the curl of our vector field. Our vector field is equal to y negative x squared x cubed. So let's just set up our determinant real quick. So the first row is I hat, j hat, k hat. Second row is your differentiation operators, and the last row is your vector field. All right. So that with respect to y 0, that with respect to 0 to z is also 0. So there's no I hat component. That and that. Okay. j hat. Okay, so there's a j hat component, seems like. See what k hat offers or has to offer. Okay, that's not 0, obviously. Okay, so this works out to be 3x cubed. That works out to be 0. This works out to be negative 2x. That is negative 1. Right, so we can write it as a vector so that it looks something like this. Right then. No, that should be the curl. Okay. Let's just box it for now. Okay. So our surface was z equals x squared plus y squared underneath the square root. We can parameterize this as r cos theta r sine theta r. And the normal of that is cos theta sine theta 1 negative r sine theta r cos theta 0. It's gotta be a determinant. Okay, I'm gonna go along that way this time. So it's gonna be k hat r. I'm gonna evaluate the determinant that way. So that's the minor for k hat. That's a minor for 1. How would this go? R cos theta I hat minus r minus negative r sine theta j hat, and then 0. Okay, so if we, hold on a second. No, I think this is right. Okay, those become positive, and what we end up with is negative r cos theta I hat minus r sine theta j hat plus r k hat. So what direction is this normal vector pointing in? So if you guys remember from before, this is how our surface kind of looked like. This normal vector has a positive z component, negative y, and negative x component. Let's draw a section view of this cone. If it has a positive z component and a negative x component, it's pointing inwards. And that is all right, like big deal, if our results from the surface integral is positive 9 pi, then that just means our normal vector was pointing the wrong way. And that's totally fine. So let's move on. Okay. This is our curl, and this is our normal vector. Let me write it a little neater. So what we got to do is we got to substitute these values in terms of r and theta. So x was equal to r cos theta, that is equal to negative 2 r cos theta minus 1. Now we just got to dot the 2. That's 0. That's irrelevant. These two become 3r cubed sine theta cos squared theta. These become negative 2r cos theta minus r. Okay. Seems like an ugly integral. Okay. So theta goes from 0 to 2 pi. And r goes from 0 to 3. Okay. This becomes... Now let's look at this function here. Sine theta cos squared theta integrates to negative cos theta cubed divided by 3. This evaluated from 0 to 2 pi is equal to 0. Because essentially you're evaluating cos theta at the same value, but in a different period, and then subtracting the 2. So that's just 0. This cancels out. This doesn't. So let's work on it. Maybe this cancels out, but we'll see. So this is negative 2r squared. Integral of sine cos theta is sine theta, going from, and it's going to go from 0 to 2 pi. So it does cancel out because essentially you're evaluating a trig function at the same point but in different periods. So that's 0. So all you have left is negative r. This doesn't have a theta term in it, so just add a theta when you integrate. Go from 0 to 2 pi. And then dr, still have one more integral, like still one more variable to integrate with respect to, so yeah, just throw that in. This becomes negative 2 pi, or 2 pi r. Got another variable to integrate with respect to. This then becomes negative 2 pi times r squared divided by 2. And you're going from 0 to 3. 2's cancel out. And all you're left with is negative 9 pi. So that's exactly what we got with the line integral before. Yeah, so that's what we got with the line integral. This is what we got with the surface integral. That means the left-hand side of the is equal to the right-hand side for Stokes' theorem, meaning that we've successfully proven that it works. So yeah, it's kind of hard to make a summary for this video because I don't really know what Stokes' theorem is for. My professor just showed this formula to us and asked us to prove that the left-hand side is indeed equal to the right-hand side. So yeah, I guess just as a summary, all I can say is, so Stokes' theorem is for open surfaces, not closed surfaces. So tennis ball is a closed surface. That means you can't use Stokes' theorem for it. A Coke bottle, however, is an open surface, so you can use Stokes' theorem for it. Yeah, and the surface integral is supposed to be set up for the surface of your surface, I guess. And the line integral is supposed to be set up about the edge of that surface. Yeah, that concludes the Stokes theorem video. See you guys in the next one.